So today we're going to graph quadratics and they're going to be written in standard form. And in case you're wondering what that means, it means that all the graphs we see today are going to be written in this format. So quadratics come in a lot of different flavors, types. The one that we'll start working on, oh, I'm going to throw out a guess here that it'll be Monday. I'm just kind of guesstimating. But the next one will be vertex form. And you don't even have to write that down, but just know you'll like it a lot better. And then the last thing we'll do is a conversion that you'll appreciate, but that's several days away. So today we're just going to focus on this, and there's parts of this that you're going to not have issues with, and there's parts of this that you're not going to like very much. There's a lot of um, very basic math, like multiplying fractions by two and then dividing something by a fraction. Copy dot flop. There's a lot of those sort of basic skillsy things that you won't need a calculator for anything that we do, but still, just if you're the kind of person that struggles with the basic annoying math stuff, then there'll be parts of this that you kind of go, yeah, that was dirty. Because it's inevitable. So we're going to start with nothing dirty at all. So the first example, I've got these lined out, is this one. So every quadratic that we graph will spawn from this. This y equals x squared is called the parent. And, you can call it the parent graph, the parent function, whatever, but every family, when you graph, like if we have time to get to cubics, quartics, square roots, like we won't do probably logs, I don't think, exponentials, absolute value, like there's tons of different types of graphs. They're called families of functions, and every family has a parent. And all the other graphs in the family are spawns, like offspring modifications of the parent. So the first mission here for the first 5 minutes is to make sure that you have no issues understanding why the parent function does what it does. So the only way for me to make sure that this makes like stick in your head sense is for the first time we do this to make a table. And honestly, we're not going to make a lot of these tables going forward. But I think for this first example, you should, and I left room on that graph paper I gave you, so you should have room to kind of write down the things that I write down. Do you guys know what the shape is called when you graph a quadratic? All quadratics look the same. They point in different directions. Some of them are wider, like fatter. Some of them are skinnier, but they all have a shape. Anyone, it starts with a P. Have you ever? Yeah. Every quadratic that you graph will form a shape that we call a parabola. Okay. And parabolas, they're predictable. They have a high point or a low point, and they all look like either arches or bowls. So a bowl takes on a shape, well, you'll see, and an arch like the arch, like in St. Louis or McDonald's or something like that, is like an upside down bowl. So it like has a top and then it curves down like that. Okay. So like if you went to St. Louis and looked at the arch, that's an example of a parabolic structure. Okay. And you see them all the time. If you watch like NFL games, the guys or gals on the sideline with those big, funny, like cone shaped microphones. Have you ever seen those guys? They work like for NFL films. They're really good at like picking up all the sounds on the field. Those are called parabolic microphones. If you took a snowball and threw it and you videotaped it from the side, the flight pattern of that snowball would be parabolic. All right. There's examples of parabolas all over the place in the real world. So anyhow, let's get to the math of this. Okay. So to make the first graph make sense, we're going to make a table of values. And you know how tables work. This is old school math. You just pick X's, put them in, and you get Y's. Like that's how functions work. You feed them and they give you back. So let's say we put in 0. And when I say put in, what I mean is we're going to put numbers where that green arrow is pointing, right? Easy math. What's zero squared? Zero. So we can then say that the point 0, 0 is our very first point on our very first parabola. So on our first graph, we're going to go to the center, origin 0, 0, and we're all going to make a point. Now the next, and I'm not really going to leave it up to you. I'm just going to kind of boss you. The next one that I think we should use is 1. Again, math is easy in this case. What's 1 squared? 1. So we now know that there's also a point at 1, 1. So if this were like simple algebra 1, we might already make a theory, a conjecture that, oh, it's just a straight line that's going to keep going like this. But because of the exponent, quadratics are what we call power functions. So anything that has a power isn't going to behave like a line, right? Because exponents have stronger effects as numbers get bigger or smaller, right? For example, if we put in 2, what's 2 squared? 4. So you can see that the rate of growth changes. We're not going to follow the same pattern of right 1, up 1. Now, when I go to the right 2, I have to shoot all the way up to 1, 2, 3, 4. So you can start to see that curvature I was talking about taking place. The only other one that will fit on this grid, it just is convenient for us, on the positive side is 3. And what's 3 squared? 9. So we can now say that there's also a point at right 3 up 6, 7, 8, 9, like this. But something interesting happens when you head the other way. So if I head to the left, which why not, right? There's no domain restriction on this. There's no law that says I can put whatever I want in place of X. I'm just picking good ones that are easy for us. What if I put in a -1? What's that when you square it? It is. It reflects back up to 1. So we can now say, oh, that's cool. So if I go left 1, I can also go up 1. And you start to see it taking shape. This is how parabolas take their form. That X squared causes symmetry. X squared is a really cool. 2 is a cool exponent because he makes negatives become the same as positives, right? What if I put in a -2? You get +4. So now I can go left 2 and up 4. And you see the symmetry that I was talking about. And then, of course, no big secret here. If we put in, run out of room here. If we put in -3, what do we get? 9. 9. And there'll be times when, maybe we'll have an occasion where we could have a little bit of we can change our axes, what's called a scale, make every X and Y worth like 2 or 5 or 10 or something if I wanted to fit more points, right? But in this case, since I'm just kind of bound by ones and ones, I'm at my limit at this point because I can go left 3 and I can go up 9. But that's the extent of what I can do. What you'll come to find after today in about 20 minutes is that it's not the math generally that's the worst part. It's the trying to make this not look like crap. So now and I'll take one for the team here and make a fool of myself. We have to try to graph this, and it's harder than you think. So I would recommend that you use a pencil. And what I like to do is I like to just kind of, it's hard at first to create it. First off, you cannot graph it with straight line segments. Like that's going to get you in trouble. There's no point on a parabola at which it's going at a constant rate ever. Okay, it's always changing, and that implies curvature. And so what you want to do is just start trying to make it look like it's curving as it goes through all the points. And I'd say that one was actually pretty good. That was a good way to start the Wednesday there. And then you got to nail it on the other side too. And it's not, if you feel like you want to say something like, I'm really bad at this, well, you're preaching to the choir. It's very hard to graph these. You will find throughout today and tomorrow that the fatter a graph is, it is honestly easier to graph. I don't know why that is, but I think it just allows for more freedom of pencil movement when you see fatties. But this normal one and anything skinnier than this, they're kind of hard to graph and they're hard to make look decent. So I'm not going to ding you for minor artistic deficiencies. Let me tell you what I will ding you for. These are the 2 things that will get you, bless you. Are you listening? These are the 2 things that I have to take points off for. Number 1, if it looks like your graph is going straight, I'm going to ding you. These are not V's, they are curves. And the other thing would be this, and it's a very common occurrence, this happens a lot, is that people their pencil comes up and then they go like this. I will tell you, as minor as that looks to you, that's mathematically criminal to think that something could come back on itself like that, right? We know functions don't behave that way. So what you want to be mindful of is, yeah, you want to get better over time at making your graphs just generally look good. You'll know when you look at it, you'll be like, man, that's a nice parabola. But the ones that will get you busted are the straightness and the horseshoe when it comes back on itself. Not allowed. Okay, those are mathematical offenses, not artistic offenses. That is the graph of y equals x squared. That is the parent function. Everything we do now, today and tomorrow, and like I said, for the next week and a half, will be that, but different. Any questions about y equals x squared? Okay. The other few real quick that I decided we should knock out before we get to the hard stuff is
We are currently in a hold. Stay in your room and follow the hold. Thank you.
so this one we can also make a table for, but eventually, again, we won't have to do this. But what happens is when you have a negative in front, is basically the x squared is going to behave the same way, right? So maybe we don't even need a table, but what do you think a negative in front does? Say again? The graph's going to go down, right? So the one point that's not affected by that is a vertex. I should have said that. That bottom point that we just graphed, that's called the vertex. It's like the corner, kind of. And so in this case, if I put in 0, I still get out 0 because the negative of 0 is, well, still 0, right? But again, you think about this. If I put in 1, the red egg, 1 squared is 1, but then the negative comes on and says, I'll make you negative. We're not squaring negatives here, right? I'm squaring 1 and then making the answer to that negative. So the same could be said for 2. If I put in 2, yeah, I get 4, but then the negative comes on and says, ha ha, you cannot defeat me. And then the same for the 3. He makes a 9, but then gets negated to be a negative 9. So like, I think it was Nick that said this, what's going to happen is our graph is just simply going to reflect now. So we're going to go right 1, down 1, right 2, down 4, and right 3, down 5, 6, 7, 8, 9, like this. Okay. And the same can be said on the other side if I go to the left. If I put in -1, you got to be real careful. I would draw that red egg in my notes if I were you. It's really important that you respect the order of operations. Sometimes people say, but it's the negative of a negative. And I'm like, no, it's not, dude. You take -1, put it in the egg. What's -1 squared? It's 1. But then that negative comes on and says, I will rule you. One negative to rule them all, right? Like that negative says, you cannot defeat me with your dumb little exponent. So yeah, we put in -1, square it to get 1, but then the negative comes on and says, ha ha. You can't fight that negative. The one with the red arrow up there, you can't beat him. He's going to say, do whatever you want. I'm going to make your answer negative. Um, so all of our points over here are going to be reflections like this. Okay. And I don't feel like I want to take the time right now and draw that, but do know that it's obviously incomplete if you don't draw the curve, right? This is 7 points out of an infinite number on this graph, but we'll just leave that one at that. Any questions on that one? And the other two things I wanted you to see before we get to the hard ones. Are you okay, Landon? You don't like my green pen?
No, I'm a white. I couldn't see it.
Oh, sorry, buddy. Do you want me to go back?
Yeah.
Do you want me to make them different colors? Yeah, I can do red. So is that better? Thank you for the input. That helps me. So is that better?
Yeah.
Just FYI, they're literally the exact same points as the one we did before. They're just upside down. That's what the negative in front does. He's a flipper. We call that a vertical reflection, vertical flip. Good. All right, on to number 3, and these are just our warm-ups. The next one I want to talk about with you is this one. This is y equals 2x squared. So here you're going to see your first vertical, what we call either a stretch or, bless you, a stretch or a compression. So let's take a look at how this gets affected. So we'll make tables on these first ones. Same kind of speech here. If you put in 0, make sure you embrace the egg. If you haven't drawn the egg yet, You really should. It's a good reminder of the order of operations. So put zero in the egg. What's zero squared? What's two times zero? Zero. So we still get zero. So I can put a point at 0, 0. But watch what happens now. Something's going to change. If I put in one, what's one squared? One, right? Yay. But then what's two times one? So you just saw your first example of a vertical stretch. What happens is if you can imagine like imaginary hands grabbing your parabola and actually stretching it like silly putty, like pulling it upwards and stretching it. And it's going to create this, the sense that it's getting skinnier. It is. It gets skinnier when you stretch it like anything. Try anything you want. Again, grab some silly putty and draw a shape on it or something and then stretch it. And you'll be like, hey, it got skinnier. Yeah, that's how it works. And then the same, we're going to run out of space pretty quick on this one, but if we put in two, what's two squared? Four, and what's two times four? Eight. Good. And so you can see now that we're going to go out of real estate here because 1, 2, 3, 4, 5, 6, 7, 8. I'll just show you why we can't graph another point. But if we put in three, what's three squared? And 9 times 2 is 18. So we don't have enough real estate. You'll find that often to be the case with vertical stretchers, is that you just run out of space quick. There will be parabolas where you can only graph a couple points, quite frankly, like this. You graph the vertex and then maybe one or two more. And then obviously I can reflect. I don't think I need to go through the math of it with you, but if I go to the other side, obviously it's going to be the same verticality, right? Like that. Good, good. And then the last of our warm-ups is this one. I want you to see what we call a vertical compression before we get to the fun. So in a case like this, we think about, just again, the math, draw the egg. Can't stress enough the egg. Don't do the number in front until you've egged it. So if I put in a 0, again, the vertex won't change. What is 0 squared? 0. What's a half of 0? Still 0. Shocker, right? But then something kind of interesting happens. If I put in 1, what's 1 squared? 1, but what's half of 1? 0.5. You could call it 0.5 or you could call it 1/2. But what you see now is, hold on, it's like the man keeping me down. This time, instead of stretching your silly putty, you're actually pushing down from the top and pushing up from the bottom, creating the illusion that it's being squashed. And so now when I go to the right one, I only go up a half of a unit. So this is an example of what I like to call a fatty. So let's put in a 2. Do the egg. What's 2 squared? What's half of 4? 2. So now when I go right 2, my vertical amount is changing, right? So I go right 2 and I only go up 2. And this one I can fit more points this time. Vertical compressions allow us to graph more points. If I do 3, what's 3 squared? 9. What's half of 9? 4.5 or 4.5, you pick. So now when I go to the right 3, I can go up 4, 1, 2, 3, 4.5. So you see that this bowl is opening wider. He's growing less quickly. I can do more. What's 4 squared? 16. What's half of 16? 8. So when I go right 4, I can go up 4, 5, 6, 7, 8. And we are now out of room. Just show you that if we tried 5, what's 5 squared? 25. What's half of 25? 12.5, right? And so we're out of room. But you get the idea that this is a wider parabola. And then to save some time here, you would, I hope by this point in the lesson, agree that the same mathematical outcome is going to happen when we go to the left, right? The squared is an amazing magic, man. You square a negative, it becomes a positive, and then you find yourself doing all the same math again. So I can just repeat these points on the left. If I go left 1, I go up a half. If I go left 2, I go up 2, my bad. If I go left 3, I go up 4.5. And if I go left 4, I go up 8. And you can clearly see that that is a much wider parabola than its predecessor. Good. Okay, so now we get to the hard part. So that's your warm-up. I hope I haven't overwhelmed you with that. That's the nuts and bolts basic quadratic graphing 101. Bear in mind why they do what they do. Okay, the parent function and then everything you're going to see is just a modification of the parent function. So for this, what I want to do is go back before we start, and I want to look at some really important things. And I'm going to zoom in on our first graph. So I want you to memorize some numbers for me. These numbers are going to define your success. What is the length of that vertical climb right there? You should write that down. That's important. 1. These are going to be our standard growth rates, our standard growth amounts. But I'm going to mark the next one too. What's the length of that growth rate or that growth? 4. Write that down. These numbers are going to become your bestie friends. They're going to save you so much time. What's the length of our next vertical growth? 9. You know this. And if you ever forget these, it's just 1 squared, 2 squared, 3 squared. If I had enough room on this graph, how high would my next point be up here? Saying 16 tells me you're not lost. Very good, because 4 squared is 16. So the numbers that we're going to really embrace now for the course of this next week or 2 weeks are these. I would write them down. When I go out 1, my vertical change is 1. When I go out, notice I'm not saying right or left because these are symmetric. Out means right or left, right? We go both ways. When I go out 2, how far up do I go? 4. When I go out 3, how far up do I go? If I go out 4, how far up would I go? If I go out 5, how far up would I go? Good. And listen, these aren't really hard to memorize. What are these numbers? Yeah, they're the red list numbers, right? They're squares. So it's not like you have to like memorize them. You will, but if you forget them, they're just the squares, right? 1 squared, 2 squared, 3 squared. Having said that, let's do an actual quadratic now. So clearly we're not going to have work time today. I'm looking at the clock here and I've got 10 minutes, which yes, that's okay. Try to get through as much of this as I can, and then we'll just have a nice solid chunk of work time tomorrow. So yeah, so these are a little bit harder. So what you notice right away is that there's a whole bunch of extra stuff after the quadratic term. And the main objective here is the answer to this question. I cannot stress enough how important, and this is going to become such a staple in your math life for the next while. Can I find the vertex? The thing about quadratics is they're predictable. And if you can walk me to the vertex, that high point of the arch or the low point of the bowl, I can take it from there. So the question is always, how do you find the vertex, right? On those last ones, it was easy because it was always at 0, 0. That was easy. But what's going to happen now is the vertex is going to start hopping around. He might be to the left 4 and up 5. He might be right 2.5 and down 6.3. There's a way to do this. This little purple formula is going to be your other best friend. Write this down. The x coordinate of your vertex can always be found using this formula. And someone who's very observant and mathematically bold and confident would notice that I've seen those before. I've seen negative b over 2a. When? Where? It's in the quadratic formula. It just doesn't have the discriminant. It doesn't have the plus or minus the square root of b squared minus 4ac because that part is 0. Neat. So this is just a little baby portion of the quadratic formula being pulled out, which helps us a lot. So using negative b over 2a, you can find the vertex of any parabola written in standard form. In this quadratic up here, we all would agree that our a value is 1, right? What's our b value? Correct. And our c value is IDC. The thing about finding the vertex is we don't care about the C value. So you want to write 22, you can. It's just something I'm not even going to really address. Don't care. Okay, we need A and B. So having said that, we're going to do some math. And the math is going to start easy. And it's good. This is the part that's going to get a little bit under your skin here. So this one's a warm-up. This is easy. So if I plug B and A into this formula, what would the top of my fraction say? What's negative B? Negative 10. And on the bottom, if I multiply 2 by A, what do I get? What is negative 10 divided by 2? So here's the upshot, dudes, dudettes. Your vertex is at the point negative 5, comma, don't know, IDK. but we at least now know, bless you, where the vertex is horizontally located. He's going to be somewhere left 5. Any thoughts in math? You know this from hanging out with me for years. How in math, if you know an X, can you find a Y? Plug it in. Yeah. Go back to the equation up here in the white box and just put in an X that you know. It's math always works this way. If you want a Y, just stick in an X. Feed it. So let's do some math. I'll start with a red egg. If I put -5 into the red egg, what do I get? I'm sorry, what?
Right.
I get 25. Good. If I put -5 into the yellow egg, what do I get? -50. And I don't have any input for the C value, so he'll just be a constant value of +22. And I say this is where if you struggle with simple math, then I'm sorry, but it is what it is. We have to math. What's 25 minus 50? -25. And what's -25 plus 22? We now know that the vertex is at -5, -3. And as you'll see, that's massively important because, like I said, I can take it from here. So let's all go left 5, down 3, and graph our vertex. So 1, 2, 3, 4, 5, 1, 2, 3. Now, what I want you to do, I hope you're not lost yet, is consider the equation up there in the white box. I'm going to draw a very obnoxious purple arrow. So I guess I'm drawing a red arrow. Do you see any number in front of x squared? I don't either. That means this is the parent graph in a different location. So what we're going to do now is we're going to use our 1, 4, 9, 16 knowledge and just graph points without making a table. You don't have to do any more math now. So check this out. I'm going to go to the vertex, which is right here, and I'm just going to do my thing. I'm going to go out 1, up 1. See this? I'm just rebuilding the parent function from a new home. When I go out 2, how far up am I going to go? 1, 2, 3, 4. When I go out 3 from my vertex, how far up am I going to go? 2, 3, 4, 5, 6, 7, 8, 9. And in this example, I do not have enough room to do the next one because if I left and went out 4, how far up would I have to go? 16. And I can't quite make it on this piece of graph paper, but that is how you graph a parabola. It's just operation find the vertex. I want to start one more. I've got about 3.5 minutes, which is, I've been doing this long enough. I should know that these things take time, but I naively hoped we could get through a few more than this. So let's try one more. Let's do my second one that I have marked is y equals -x². And we are going to have to take some notes at the start of class tomorrow. I apologize. So this is our next one. What is A? -1. What's B? So we're going to use our best E formula, -b over 2a. Math with me. What's the negative of B? -2. Over, what's 2 times A? -2. And what's -2 over 2 reduced to? 1. So we can now say that the vertex is here at this point that I just wrote in green, with half of itself conspicuously, of course, missing. But for the 804th time in our existence, how do you find the y? Plug it in. So we're going to go first into the red egg. And we're going to put the number 1 in the egg. What's 1 squared? What's the negative of 1? -1. So the red part is -1. Now we're going to go into the yellow egg. And we're going to put 1. What's plus 2 times 1? Last I checked, 2 times 1 is 2, right? And then I'm going to go to the back end here. The green egg, remember, will be your constant. He doesn't care. He just says, I'll just add me or subtract me, right? What is -2 plus 1? Negative -1 plus 2 is 1. What's 1 minus 1? So we now know the vertex is at 1, 0. So this one, he stayed close to home, but his vertex is the key. So I'm going to go to the right one, and I'm not going to go up or down. You're going to do the same thing. And tell me about the graph. Let's see if you've learned. Tell me about the graph I'm going to draw.
Just another reminder that we are in a hold, so keep your students in your current classroom for second hour. Thank you.
Hey, you get to take more notes. Yay. Tell me about the graph. Do you want another arrow? Here, I'll make it less fat this time. What's in front of the x squared? And what effect does a negative have on a graph? It goes flippy doopy. So we're just going to graph the exact same default parent function in a downward direction. So again, I'll zoom in a little bit, and we're just very simply going to go like this. We're going to go out 1, down 1.
That's fine.
Turn that frown up. Wait, never mind. Yeah, it doesn't work. Thank you. You said it the right way. And then we're going to go right 2, down 4. And then we're going to go right 3. And notice when I say right, I'm going back to the vertex every time. Our outward motions reset from the vertex, okay? Don't build off of where you've already been. Always reset to the beginning. So from the vertex, if I go out 1, 2, 3, how far down do I go? 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, you can clearly see that we are out of real estate here. So I have no idea how long this hold is going to last, but I'm going to milk this for whatever it's worth. So how are you feeling so far?
Good.
Okay, there is about a 77.93% chance that you're not going to care for these last examples very much, but let's see how much progress we can make. Yeah, so stay here, okay? You heard the lady. So we're going to do y equals 1/4 of x squared minus 3x plus 7. Ready? What's a? 1/4. What's b? -3. And c, remember, doesn't matter. So we're going to use our bestie formula, negative b over 2a. And this is the part that I fear you're going to like the least. Listen, if a minute from now or 2 minutes from now, you can say to me, well, that wasn't bad, then we're over a huge hurdle. This is the part that scares me as your teacher, just because I think year after year, basic skills tend to go by the wayside. I think generationally, we get worse at basics every year as we rely more on technology. But the basics are critical. So here it goes. If I do negative b on top, I get 3. Right? It's this part, which I wish this wasn't a thing. It just is. Can anyone tell me what 2 times a equals? Yeah. And I just feel like that's something that a lot of people ask about. Like, how did you get that? So I'm going to write it down, and then I'm going to show you how Will and I, and maybe a few others of you got this. This is what 2 times a looks like. It's a half. And just to refresh you on your basics, when I do 2 times a half, I'll write it in yellow. This is what it looks like. This is what 2a looks like. It's 2 times a, like that. And years ago, when you learned about fractions, what did someone teach you when you're about to multiply something by a fraction? What do? You put it over 1, right? Fractions need fractions. So this 2, I'm going to say, you're not really, I'm not going to write you as a 2. I'm going to write you as a 2 over 1. You're going to be doing a lot of this. And you could reduce now or later. What's 2 times 1? 2. 1 times 4, 4. 2/4 reduces to 1/2. Any stress there? Okay. But we're not out of the woods yet, because now we're like, oh, I see what you're doing to me here. This is a 3. Oh boy, I'm going back to yellow again. This is a 3 divided by a 1/2. And then again, all of our training, our basic elementary school training kicks in. How am I going to do a whole number divided by a fraction? I'm not going to go there. Okay. That I appreciate the sentiment, and if that works for you, but I don't want to cross multiply. Let's proper this so that everyone is on the same page. What's the first thing I do with the 3? put it over 1. And then you remember copy dot flop, right? So we're going to change the division to a times, and we're going to rewrite the 1 over 2 as a 2 over 1. And what do we get? 6. 6 over 1 equals 6. So we can now say, based on that little basic skills jungle that we just kind of drudged our way through, that the vertex officially lies at the point 6 comma blank. Got it? That's the first little jungle that we have to try to machete our way through. Here comes the next one. The eggs. Critical. Red egg. 6 is our guy, right? We're trying to find his mate. Every X has a partner Y. In a continuous function like this, every X has a mate. So when I put 6 in the red egg, what's 6 squared? 36. What's a fourth of 36? So I have 9. Let's go yellow egg. What's the yellow egg equal? Negative 18. And then, of course, the green egg gives 0 craps about whatever's going on over to his west. We're just going to add 7. And then you basic math. You just can never, you see why it's critical. You never ever let yourself say something terribly dumb like 9 minus 18 is 9. What's 9 minus 18? Negative 9. And what's negative 9 plus 7? We now know the location of the vertex. Finding the vertex can be a little bit more of a chore when there are fractions involved. But we're done now. The problem is at this point effectively over because all the hard work is done. There are 2 parts to this. There's the map to the job site. That's the hard part. And then there's the blueprint once you get there. Tell me what to build. Building is easy. Let's get to the vertex. So we're all going to go right 6 and down 2. 1, 2, 3, 4, 5, 6, down 2. And wahoo, we know where our graph is. Talk to me about my graph. Does he open up or down? Why do you think he opens up? Because there's no negative in front. I will draw an obnoxious purple box for you just to really draw your attention to the only number now that matters. He's your builder. He says I'm positive, so it's going to be a bowl. What else, though, from earlier in our time together does he affect?
Oh, shoot.
You remember this. You remember it from one of our examples when I put a 1/2 in front of the x squared. What does that do to the bowl? It chunks it. It makes it fatter. It makes it grow less quickly. So now what we normally would do with our 1, 4, 9, 16, 25, 36, 49, 64, our Y value growth thingies normal are going to get chopped down divided by 4 because we need a fourth of them all. So I'll zoom in on this nice and tight for you here so you can help me with the math. So here we go. From the vertex, normally when I go out 1, I would go up 1. I'm going to go a fourth of 1, which is right about here. See how easy that is? Normally, when I go out 2, I would go up 4. But what's a fourth of 4? 1. So I'm only going to go up 1. You see, we got a real chunker here, huh? Normally, when I go out 3, you basic skills people get to shine here when I ask you a question coming up. Normally, when I go out 3, I'd go up 9. What's a fourth of 9? God, don't say that. Come on, what's a fourth of 9? If you had $9 and you were going to divvy it up into 4 piles, how much you put in each pile? Did you just say 1.5?
Oh, no.
Take that back. 9 divided by 4. Yeah. 2.25. That's what I'm talking about. $9 divided by 4. Everyone gets $2 and an extra quarter to make the extra ninth dollar. So I'm going to go out 3, and instead of going up 9, I'm only going to go up 1, 2.25 like this. You see what I mean earlier about how basic skills are going to really either help or hurt. And let's do another. If I went out 5, nope, sorry. If I went out 4, how far up would I normally go? 16. What's a fourth of 16? 4. So I'm going to go out 1, 2, 3, 4, up 1, 2, 3, 4, like this. And just because I'm out of real estate on the right side doesn't preclude me from doing more points. Let's do another one. If I go outright, if I go 5 squared is, so we got a normal 25. Let's do better this time. What's 25 divided by 4?
Good.
Uh, so I'll record this one. So we're gonna do this one that has a lot of fractions in it. So sorry, not sorry.
Oh, no. Oh, no.
I will say this, for whatever this is worth, when you see me putting fractions back here, you probably initially perceive it as, oh, that's terrible. Thanks a lot, Jerko. I'm actually doing it for a reason that you'll soon understand, and that's to cancel out another evil. You'll see. So, ready? Here it goes. What's A? What's B? So here we go. Basic skills, hell, incoming. Opposite of B divided by double A. Here we go. What would I write for the opposite of B? The opposite of B. Negative 1/2 goes on top. Opposite of B. On the bottom, what is 2 times A? Negative 1/2. Got it? Now, if I put this into play, what's negative 1/2 divided by negative 1/2?
1.
Yeah, anything divided by itself is just 1. So my vertex is at the point 1 comma something. And we're not out of the woods yet. Sorry. Red egg. What's 1 squared? What's negative 1/4 times 1?
Bigger one.
Good. Green egg. What's 1/2 times 1? And then, of course, the yellow egg is like, whatever, just copy me down. All right, now you got to go all the way back to 4th grade when Mrs. Darkenstuken taught you about common denominators, right? What is negative 1/4 plus 1/2? I have to change 1/2 to have the same denominator, 2/4. What's negative 1/4 plus 2/4? 1/4. And then you can see why minus 9/4 turns out to be your friend, because what's 1/4 minus 9/4? Negative 8/4, which equals negative 2. So again, to my point, that fraction at the end was just there to help you in the end, not to annoy you. He helps. He's like, I'll bring you back to whole numbers. Like, hey, thanks, buddy. So our vertex turns out is at 1, negative 2. So we're going to graph it. I'm going to graph it super fast. I'm going to go to 1, negative 2, and then we're going to look at the structure, the builder. Who's my builder? Yeah, so I'm going to erase everything on the TV right now, except for the one number that I need to live. Nothing else matters. The guy that was in front of x squared, he's your bossy. Tell me about him. If he's negative 1/4, what does that mean? It's going to go down and he'll be a fatty, right? So let's get there. Let's get zoomed in a little bit. So I'm going to go out 1, down 1/4. I'm going to go out 2, down 1/4 of 4. I'm going to go out 3 and down 1/4 of 9, which is 2.25, and so on and so forth like that. So, okay. All right. I'm going to pause this. Boy, you guys got a long bonus lesson today. You're lucky. Seriously, you should listen. You really should listen.
Listen.
I'm just looking at J-Ball back there.
Ball.
You really should listen. Jesse? You are used to simplifying equations. We just got done with a unit where we could divide everything by 2 because it was sweet, right? The reason we were able to do that is because where you currently see a y, there would have been a 0. And what gives us that flexibility to divide is that 0 can be divided by anything and remain unaffected, right? But in a case like this, if you try to divide everything by 2, then you have to divide the left side also by 2. And unlike a 0, he gets affected. And this is no longer in function form. It's going to say y over 2 equals what you want. And then we're in nowhere good. Okay. So no, the answer is no, emphatic 36-point bold italicized underlined font. You cannot divide all of the terms by something. Okay. It will affect what happens badly. Great question. Thank you for asking that. What a glorious question.